All right. Good morning, everyone. Welcome to the California Climate Policy Modeling webinar. My name is Anthony Eggert. I'm the director of the UC Davis Policy Institute for Energy, Environment, and the Economy. We've got a lot of material to cover today, so I just want to provide a couple of opening remarks and then turn it over to my colleague Sonia for a few as well, and then turn it over to our presenter, Jeff Morrison. Just in terms of how this is going to go today, this is a webinar. It is being recorded. There are options for you to ask questions. You can type in the chat box, which is on the lower left hand if you're logged into the ReadyTalk software. Alternatively, you can raise your hand, which is a button on the upper left, and we can unmute you to recognize you for a comment or question. We're hoping that the presentation will take about approximately 30 minutes. So we'll leave plenty of time for questions, and looking forward to your questions. Any that we do not get to during the 1 hour webinar, we can potentially follow up and answer those for you. So the Policy Institute is an initiative of the campus to leverage university expertise to inform better policy. We work with partners across the campus to make sure that their research is addressing the most pressing societal issues and those of the most interest to the policymaking community. And then we work with them also to make sure that it is delivered into the policy process and informs that process with the best available science and research. In this particular project, the California Climate Policy Modeling project has been informed by a wide number of folks, and we just want to thank them. This includes the steering committee that contributed to the forum that we'll be presenting the summary of today, as well as all the modeling teams, without whose work this would not have been possible. So we really want to thank those, as well as the funders for the workshop that we held, which included PG&E, the Energy Foundation, and the Environmental Defense Fund. The goals of this really were to try to use modeling to improve our understanding of what was possible with respect to reducing greenhouse gas emissions in California. What were the likely trajectories, what were the technologies, the strategies that would be possible and plausible to get us there to the goals for long-term climate stabilization. And particularly to focus in on a midpoint of 2030, and we'll discuss a bit more about that in the slides. I would say that the main thrust of this was to really figure out how to best use models to inform policy. Really, models, one of the analogies at the forum is that they're a platform for a conversation. They provide you a tool and a language with which you can test various assumptions and ask what-if questions. And it provides, if done well and transparently, a way in which policymakers and experts can basically understand and determine what are the implications of different policies and different strategies. Let's see. The agenda for today, like I said, just a quick introduction here before I turn it over to our presenter. But before I do that, I want to introduce my primary partner in this project, which is Sonia Ye, who's a senior research scientist here at UC Davis. Sonia?
Okay, thank you. Now I'll just say a few words to kickstart the meeting. I'm Sonia Ye, a researcher from Institute, the Next Step Institute of Transportation Studies and Next Step program. We're very happy to collaborate with the Policy Institute, hosting the workshop and on the Climate Modeling Forum. And we approach this problem from different end of the spectrum. As a modeler, we've long felt the need to have this kind of dialogue to drastically improve science-based discussion for policy and improve the quality of the modeling tool. And we had a very fruitful collaboration and workshop in December, and this presentation is to summarize the results. And we look forward to hear the feedback today from all of you and expand the efforts to the next level in the coming months. Thank you.
Excellent. Thank you very much, Sonia. Okay, so and again, just to remind folks, if you have any question, go ahead and type it into the chat box. We will read those to whoever. We have actually a group here that is available to answer questions, and we have a number of the modelers on the phone that, if they're willing, we may end up calling upon them. But in addition to Jeff, who will present here in a second, we also have myself, Sonia, Chris Yang, who's a research scientist here at UC Davis, and on the phone we have Anna Maleva, who's a PhD candidate from UC Berkeley, who's worked on one of the key models that we summarized through this process. Okay. All right.
Okay.
Turn it over to you, Jeff.
Thanks, Anthony. So again, Jeff Morrison. I'm a postdoc at UC Davis, and we'll go ahead and get started here. I have about 20 slides. So this slide shows change in greenhouse gas emissions between 2000 and 2050. The state of California has the goal of reaching 1990 levels of greenhouse gas emissions by 2020 and 80% below that same level by 2050. This equates to 431 million metric tons in 2020 and 86 million metric tons in 2050. Emissions have declined slightly from earlier peaks of 2004, 2008, and we'll see if the economy, as the economy recovers, if we stay on this downward trend or not. But at the moment, the state is kind of on the trajectory to reach the 2020 target. Okay. So in this webinar, we ask how California's energy and climate systems change out to 2050 with a focus on 2030, as Anthony said. So we'll be looking at greenhouse gas emissions, fuel and technology mix that produces those emissions, and the infrastructure build-out needed to support that fuel and technology. We'll look at the assumptions that drive these results. And finally, we'll look at to what extent models agree or disagree on these results. Just as a little background, there's been a lot of talk globally about 2030 targets or so-called midterm targets, and just within the state, two documents that have come out in the last 6 months have specifically expressed the need to look at a midterm target for California. So this is in part where the intermodal comparison comes in. And before we jump into the actual comparison, it's good just to remind ourselves that systematic comparisons of energy models have been going on for a long time. Since at least the 1970s with the start of the Energy Modeling Forum at Stanford. What we've seen is that intermodal comparisons can benefit both the modelers and the policymakers. And there are kind of two levels of model comparisons. The first simply compares and contrasts the inputs and the outputs of the model. And it's sort of like a literature review article. Kind of a higher level of comparison is when you standardize the model inputs, like population, income, technological parameters, and then compare outputs. So today what we're going to do is kind of this more basic level 1 comparison, but we hope to eventually get to kind of the standardization of inputs for California energy models. Here are 13 models and reports that we've looked at in this model comparison. In most of the slides, I'll refer to the author name and the year of publication, because many of these models have older versions, and so it's good to keep the dates in order. And to the extent possible, we've made an effort to use the most recent model version of each of the models. Okay. Out of the 13 models and reports, these are the 6 models across the top that were featured in the December forum that was held at UC Davis. This comparison table has a lot of information, and you can digest it later if you'd like. Just a couple things to note. Highlighted in the red box here is the model structure of each of the models. So we have a wide assortment of model structures that we're comparing, broadly there are 3 categories. There's optimization models, equilibrium models, and then spreadsheet models. It's important to recognize that model structures answer slightly different questions, or each of the structures answers a slightly different question. An optimization model is searching for the lowest cost or maximum utility mix of technologies and fuels that satisfies the predetermined level of demand, and as well as any policy constraints you have. An equilibrium model, like the Bear model, is based on relative prices and finds an equilibrium point such that all markets solve simultaneously or reach equilibrium. So it's not necessarily trying to find an optimal solution. It's just saying when we shock a system in a given way, what happens to levels of consumption, what happens to prices, what happens to jobs. And then most spreadsheet models, take a given technological growth rate and turnover rate of buildings, electricity plants, vehicles, and also expectations about future consumption, and then just usually have a sort of a backcasting way, have a target that they're trying to reach, and then look at what type of fuel and technologies you need, and what type of turnover rates you need to get to that target. Okay. So as you can see, the different populations assumptions here, there's a range between about 60 million and 50 million. The 60 million is from an older projection from the California Department of Finance, and the 50 million is from a fairly recent projection. And why we're pointing out the population assumption in each of these models is because population and income are kind of the 2 main drivers for a lot of the consumption, a lot of what you get out of a model. So I'm not going to show the income comparison slide, but we do have that if you're interested, and there's a diversity of income growth rates over time. So most of the newer models are there in green at the bottom, and are using this lower population projection. Okay, so this is the business as usual trajectory for annual greenhouse gas emissions, and the definition of business as usual differs slightly across different models, but you can think of it as a world without aggressive climate policy, and one in which population, income, and consumption grow at historic rates. Now, there are differences between assumed efficiency changes that I won't get into, but as you can see, these BAU greenhouse gas projections, kind of the high end tend to be the older models, and the newer models tend to have a little flatter BAU projection. Okay, so now we'll look at policy scenarios, or what we call deep reduction scenarios. So all the slides beyond this, basically we're just talking about these policy scenarios, and we won't do the BAU cases anymore. Okay, so this figure shows two alternative routes from getting from 2020 to 2050. The top is a linear reduction between the 2 points, and the bottom is a constant rate reduction. And then we can place on top of those the trajectories for the different models that reach or nearly reach the 80% reduction goal in 2050. The brown and pink dashed lines here that you see at the bottom don't actually reach the 80% reduction, but they were included because they have very aggressive reductions in early years, and we'll talk about those two, the pink and the brown, a little more in a minute. So again, this figure is showing what we call annual emissions, or kind of emissions year by year. Another way to think about emissions, though, is in terms of cumulative emissions, or if you started in a given year, say 2010, and you added up every emissions, all the emissions year by year, kind of what would you get by the year 2050? And if we do that, this is what we see. So the figure on the left is the same exact figure that we were just looking at in the previous slide. I rescaled the y-axis, though, to give better visibility. So now the y-axis goes to 500 instead of before it was 1,000. So on the left is annual emissions, on the right is cumulative emissions, and all the color-coded trajectories are the same between the two figures. And so again, if we look at those, the brown dashed line and the pink dashed line, those are both from the GHGIS model, and what you see is that even though those two lines don't actually meet the 80% reduction in 2050, they do actually come out with a fairly low, especially the brown line, a fairly low cumulative emission by 2050. And this was a point that was highlighted in the December forum that we had by Dr. Greenblatt from LBNL, and other modeling teams are also starting to think in terms of cumulative emissions. So let's see. Oh, I have a pointer here, so maybe I'll point this out. So this is the brown line, cumulative emissions. What you can see, what this figure shows fairly clearly, is that the trajectories that have their emission reductions early on tend to do much better by 2050 than the trajectories that wait closer to 2050 to really make their deep dive. Okay. Let's see.
I'll just keep going.
Okay. Yeah. Okay. So I'm going to advance the slide one more here. So this is actually the exact same figure that we were just looking at. It's just a little easier to look at because now we just have a shaded band instead of each individual model scenario. And a couple important notes. When we look at the left-hand side figure for the year 2030, since there's a lot of interest in the year 2030, the band there, that blue band, spans 8% to 52% reduction in 2030. And if you just drew a straight line, that would actually kind of cut right through the middle of that band, the 8 to 52% reduction. And then just worth pointing out on the right-hand side figure, the cumulative emissions, we have a fairly wide band by 2050 as well. And again, if you drew these out another couple decades, you might get a slightly different story. There would be a different cumulative emissions based on if the trajectory is at 80% or if you've only reached 60%. Okay, so we'll move on. So now we'll look at a little bit at individual sectors. What you see here is a comparison of models for the year 2030 and 2050 for the light-duty vehicle energy use. Over on the left-hand side is 2010 values. In the black bar is liquid fuel, so this is both petroleum and biofuels aggregated together. We did that because not every model disaggregates those two. The yellow and the blue are hydrogen and electric energy. And then I should also point out we plotted the red triangles above the columns are total energy use in the transportation sector, whereas the bars are only light-duty vehicles. So the difference between the bars and the triangles is aviation, heavy-duty vehicle, rail, bus, marine. So just two comments on this figure. First, if you look at it across the year 2030, if you're comparing 2030 light-duty vehicle numbers, you see fairly similar total energy projections, slightly different mixes across models. But if you look at 2050, there's really a wide range of total energy use and the mix. And I guess that's expected. It's farther out and much greater uncertainty in the year 2050. But we'll be exploring why those differences exist in greater detail here. Second thing to point out is that again, these are all mitigation scenarios, but across all scenarios, you see a drop from 2010 to 2030 and another drop to 2050. The only exception is the pathways model, which maintains about a 2010 level still in 2050 for total energy use. Okay. So now for the electricity sector, so these box plots, so we're representing the electricity sector here slightly different than we did the transportation sector in the previous slide. But the box plots show total electricity generation for 2030 and for 2050 across all the mitigation scenarios for a given model. Let's see. So I should also note that the y-axis doesn't go to 0, so keep that in mind. And then let's see, just an example of what we're talking about here. If you look at the California Times column, which is the third from the left. Oh, right. Okay. I'll use the pointer here. So this is the CA Times. So a box plot here in 2050, this blue and white is showing the quartiles, the 25, 50, and 75% quartiles across all mitigation scenarios. And then the whiskers are the maximum and the minimum values for electricity generation across all mitigation scenarios for CA Times. And you can see some models have a wide distribution or wider distribution of total electricity generation, but most are actually fairly tight. And a lot of that comes down to how the actual model works and how it's solving what types of constraints it has built in. Also wanted just to point out on the right-hand side is the wind, water, solar model, which I haven't talked about yet, but is Mark Jacobson's model from Stanford, where they look at how would we get to 100% wind, water, solar by 2050. So all energy use in California comes from renewable energy generation. And the scale isn't big enough to show, but these two scenarios, the 2030 and the 2050 values, they go up pretty high. They go all the way to 1,380 terawatt hours by 2050. whereas most of these mitigation scenarios are coming in around 500 or 600 terawatt hours. So you know, that's just a very large value compared to the other models if we were to get to the 100% wind, water, solar. So most of the other models, the non-wind, water, solar models, are calling for anywhere between 1.5 to 2.5 times expansion in electricity generation by 2050 from today's value. I didn't point out, but the percentages on top of the boxes are the renewable percentage, the range of renewables in each of these models. And so across all models, the renewable percentage is 30 to 51% renewable in 2030, and then 36 to 96% by 2050. Okay, so we'll move on to biofuels, and across models, this is the assumed maximum availability of bioenergy. So depending on, you know, again, how the solution algorithm works in a given model, this entire amount may or may not be used. Some scenarios might use less than this maximum. But as you can see, not every model reports the same feedstock categories. Some just say what's in-state versus out-of-state bioenergy. Most models here are based on resource supply curves to get up to this maximum. So that means that, you know, there are quantities tied with prices, and that the models are using up cheaper biomass and then more expensive biomass if they need it. A couple comments here. In most models, biofuels go almost exclusively to the transportation sector, and this is either an assumption made by the model developers outside of the model, or is the result of the model optimizing and finding that it's actually cheaper to replace you know, gasoline and diesel with biofuels than it is to replace electricity in our electricity grid with bioenergy. One thing to point out, though, is that there's very little modeling done on biopower with CCS, and it is possible that you know, if you had biomass going to a biopower with CCS, that the story would change, and maybe some of it would actually go from transportation to the electricity grid. There are two scenarios in Leap Switch that do explore that a little bit, and there's one in CA Times, I think. Yeah. Okay. I'm trying to move on here. Okay. Criteria emissions. So this figure just shows you which criteria emissions are tracked in which model. We have, you know, an assortment of different ones. This was recognized in the December forum as an area that we need to do more thinking on. You know, how do we track both criteria emissions, which tend to be very localized, and greenhouse gases? How do we track both in the same model and have a model that's actually useful? And I guess, you know, just one thing worth pointing out, the wind, water, solar model is the only one that I saw that attempts to estimate lives saved and healthcare costs avoided. And so they compare their 100% wind, water, solar with a BAU case, and they come up with 16,000 lives saved due to reductions in criteria emissions, and $131 billion saved in healthcare costs due to reductions in criteria emissions. Okay, so a few observations. The first one is pretty important. So these models are all looking at potential pathways to get to 2050 greenhouse gas goals, with the exception of GHGIS. So it's very possible there are additional greenhouse gas reduction measures in the next couple decades from today that models are not using because they're focused on reaching the 2050 target. For example, if an optimization model minimizes cost to 2050, it may not employ every strategy possible in the near term. It might just be, it's just going to be trying to solve to 2050. And for policymakers, this means that there may be additional reductions on the table that are not shown in these. Okay, so also across models, there's a relative lack of economic indicators and a lack of quantification of uncertainty. My understanding is the E3 model, the version 2 of the E3 model that's coming out this year will have a stochastic dimension in it. So they're trying to incorporate uncertainty, but uncertainty is not well handled beyond sensitivity analysis in any of these models so far. And then from the December forum, we had some discussion about the need for closer collaboration between modelers and policymakers. So the policymakers can only benefit from a modeling process if the modelers are answering the most useful questions. But the modelers need access to those useful questions, and so they need to know what's on the legislative agenda. They need to know kind of what the policymakers are grappling with in order to build those models that are useful. So it's a give and take. Okay, so key takeaways here. In terms of our midterm targets, the mitigation scenarios in these various models suggest a healthy range for 2030 between 208 and 396 million metric tons. And this equates to 8 to 52% reduction by 2030 from 1990 levels. Cumulative emissions are an alternative method for evaluating a given greenhouse gas pathway. And cumulative emissions are more closely associated with net climate impact than if you're just looking at annual emissions. Let's see, electrification of end uses is a key strategy across all mitigation models. And models suggest that to get to deep reductions, we need to expand the grid between 1.5 to 2.5 times the generation power today by 2050 to get there. And then lastly, I didn't talk about non-energy emissions today, but as brought up in the December forum, just the non-energy emissions in California alone could exceed the 2050 emissions target in some of the BAU cases. So this is an area that needs more thinking and probably needs better incorporation into some of these energy models. And then lastly, I said it on the last slide, but coordination is key, both in terms of state agencies that are pursuing different goals, but also between policymakers and modelers. As a modeler, let me help you. Help me help you. Yeah. And I think that's it. So I did want to say on the Policy Institute website, there's a lot of information on there's documentation from each of the model groups. And you can read up about specific models on there. And then also, we're in the process of writing a white paper and a journal paper that'll be out this spring that'll give much more detail on this comparison.
Great. All right, thanks a lot, Jeff. A huge amount of material there, and I would say that Jeff was instrumental in really sort of pulling the summary material together subsequent to the forum. This is no small task. And also, as he mentioned, there is a website which has links to all of the models and the model documentations. And so if you want to go into the really nitty-gritty detail, you can find that there. There's also linked on the website the summary technical brief and the summary report, which has a lot more detail on a lot of these key findings. So I think now we're going to go to the Q&A. Again, just for your purposes, you're currently on mute. If you do have a question, you want to ask it verbally, you can raise your hand, we can recognize you. Otherwise, there's a convenient option in the chat box. You can type in your question there, and we can address those in turn. There were a few questions on some of the slides, and if we go back to those, I think one of them had to do with the sort of the definition of the 8 to 52% reduction in 2030, and I guess maybe just the quick answer to that is the absolute reduction in emissions below 1990 levels by 2030, correct? Yeah. Okay. We had another question about what BAU, what the differences in the BAU and what policies were included in the business as usual trajectories.
Okay.
Yeah.
So that's something that we'll be getting into more detail, and I don't have all the policies listed right now, but
Can I have?
Yeah.
So
Yeah.
California Times model is the one with the lowest BAU. So we'll probably let Chris to say a little bit about California Times BAU, which represent the lowest number among all models. Sounds good?
Yeah, sure. As you can see, our BAU emissions are relatively flat out to 2050, and that's partly due to the fact that ours is an optimization model, and so some of the higher efficiency options in the model are available and are therefore chosen by the model to in a sense to save costs. But in terms of policies, we have CAFE standards out to 2025. We have 33% RPS, which we hold constant at 33% out to 2050. We have ZEV mandates, low carbon fuel standard. So kind of sort of a generally broad suite of policies. But again, one of the main reasons for that sort of flatness has less to do with the policies and more just to do with efficiency being a cost-effective option, and therefore, you can keep that energy use relatively flat over time.
Great.
Anna could answer that same question.
We'll have to get her on. So the next question is one of definition. It's can you remind us of what BAU and CCS stand for?
So BAU is business as usual, and again, it has different meanings, slightly different meanings across models, and that's important to keep in mind. CCS is carbon capture sequestration, and is one potential mitigation strategy for use both in the electricity sector and in the transportation sector in the future.
Great. Another sort of definitional question about how are annual and cumulative emissions defined?
Okay, so let me know if this is still not clear, but annual emissions would be if we added up across all sectors in a given year the greenhouse gas emissions and said, okay, in 2013 our economy is emitting this amount. And then in 2014, our economy is emitting this amount. And so you do that year by year. Cumulative emissions would be basically if you just started at a given year. In the slides, we started at 2010. if you started in a given year and you just added those annual emissions sequentially, so it gives so cumulative emissions gives a indication of kind of how much net greenhouse gases we're putting into the atmosphere across a given time period. And in our slides, we're showing from 2010 to 2050. But again, that's those cumulative emissions, that band is going to change depending on where you set that time period. So that's important to keep in mind.
Okay, the next slide is from Steve. He's asking if you can go back to the transportation energy slide. And the question is, why does the energy go down so much by 2030 and 2050? And then another related question is, why does one model differ so much and predict higher energy use compared to the others?
Okay. So the model that has kind of the lowest 2050 emissions in the light-duty vehicle, so the columns we're talking about is CA times there at the bottom. And we're just showing two scenarios. And you're right, the total emissions of triangles are the highest among all of them. And that has to do with actually what emissions are being counted in CA times specifically. CA times counts a greater number of transportation-related emissions than the other models. And Chris, do you want to talk about that at all?
Sure.
Yeah.
Yeah. More on the LDV or
what emissions total are you counting in CA times?
Sure. So we try and track all of the transportation modes in California. So we have both light-duty cars and trucks, medium-duty trucks, heavy-duty trucks, buses, off-road and ag vehicles, as well as aviation and marine. And so in those two last categories, you can basically have several different categories. In-state travel, so trips that start and end in the state. We have trips that go from one state to another, our state to another state, or vice versa, and then also international trips. And so a lot of these models and inventories don't count those last two categories, interstate and international travel, but we actually are looking at supplying all the energy to the California energy system, and so those are planes and ships that actually have to fuel within the state, and so we are tracking both the fuel they use as well as the emissions associated with their travel.
Great. So one little technical issue we've realized is that if you have your hand raised, we're only able to unmute you if you send your phone number via the chat box. So if your hand is currently raised and you would like to make a verbal comment, please send us your phone number to unmute and recognize you in the chat box. I guess one question I had is the relative targets of other developed countries. You'd mentioned that early in your slides, but do you want to speak to that, or?
Yeah. So I'm certainly not an expert on this, but put the slide back. Okay. So we're going back to the slide here.
For the extras.
Oh, right. Okay. I don't actually see them now.
Okay, I'll do it.
Okay. So not an expert on it, but a lot of European countries right now are setting midterm targets. They have a 2050 target like we do. The European Union apparently is haggling over this right now, and several countries in Europe have individual targets that range from about 40% to 50% in 2030. Denmark was the latest one just a couple weeks ago, set a 40% target by 2030.
Great. So the next question has to do with the electrification of end-use energy. That, again, is one of the more sort of key findings of that particular slide. It says, do any of these models study the possibility of biogas in the natural gas distribution system to consumers as an option to decarbonize that sector. And then a number of follow-up questions, whether or not that's feasible, or is electrification the preferred option, because the transportation is the more compelling use for biogas.
Okay. Yeah, and I might call on individual model developers. I know the Pathways model from E3 uses a small amount of biogas. PA Times has it, and Leaf Switch, I'm not sure about. Other models I'm unsure about. I could get back to you on that, though.
So I'll just probably chime in that that's really an excellent question, because if the technology options is not in the model, it's not going to be chosen. So this is a very important question that our next step, I think, some people ask about what would be our next step. One thing we want to do in the next step is to make sure assumptions are consistent across different models and do another random model comparison.
Yep. Okay. And right now, if you give us just a minute, we're trying to unmute a couple people.
I can also speak to the answer to the question about whether biogas is preferable to electrification. At least in our analysis, the amount of biogas that's available in the state is relatively small, and so it's not going to be useful for kind of a large-scale replacement for fossil natural gas. We have production of biogas essentially from, I think, manures and dairy digesters. You could also imagine some from landfills and MSW as well, but those sources are not expected to be certainly as large as the amounts of natural gas that we could be using in the state in 2050.
So as we point out at the very beginning, assumptions are really key in driving modeling results. So models need better data, and we need more data. And so these questions are really excellent to help modelers to improve their data assumptions and to do better scenario analysis in the future.
Great. So Jeff Greenblatt on the phone, if you can hear me, I think you're unmuted if you wanted to make a comment or a question.
Yes, thank you. Can you hear me?
Yes.
Great. So actually, I have three questions that or not questions, but comments that I've accumulated. So let's see. Maybe my first one, just underscoring what I believe Chris Yang said about biogas. It's my impression also that there is not a lot available from sources such as municipal waste and landfills in the state. There's also the problem that is not especially clean, and so you can't mix it directly with the domestic supply of biogas, and it's fairly natural gas, and it's fairly costly to clean up. But there may be some technical ways to produce higher purity and higher efficiency biogenic methane, similar to how we convert cellulose to fuel. But that's a research area. And I also wanted to point out two things if we go back to the cumulative emissions slide.
Yep. 1 second here.
Okay. Actually, one comment on that, and then one comment on sort of the BAU. But let's go with that first. I just wanted to correct a small misperception possibly about what cumulative emissions are. The cumulative emissions do not represent the amount that the atmosphere accumulates, because natural sinks such as the oceans, land sinks, take up roughly half of the CO2 that's emitted into the atmosphere each year on a global basis. So I just didn't want people to think that 10,000 million metric tons would actually go into the atmosphere. About half of that would stay in the atmosphere according to the latest climate model.
Great, thanks.
Okay.
I think you had one other point.
Oh, go ahead, Jeff.
Yeah, I did. I just wanted to underscore the what some of the other BAU results were. I have since publishing my model that you report on also looked at a BAU scenario where I essentially turned off all of the policies in my scenario 1, which are pretty much the same ones that Chris Yang had mentioned are in his BAU, which gives the roughly flat line trajectory. And that corresponds closely to my scenario 1 as well, so we have a lot of corroboration there. And then when I turn all of those policies off, like the low carbon fuel standard, the vehicle efficiency, the RPS, et cetera, I get a curve which is very similar to that blue curve by Nelson and Way. So just wanted to point out that we're getting similar results.
Great, thanks a lot, Jeff. And that was Jeff Greenblatt from Lawrence Berkeley National Labs, who had done the modeling for the GHGIS and has also contributed to some of the leap switch work as well. So I'm actually now going to go ahead and unmute Max Way. Let's see, you should be unmuted now if you can hear me, if you want to make a comment or a question. Max?
Yes, do you hear me?
Yes.
Yeah, thank you, Jeff. I'm also at Lawrence Berkeley Lab, so Jeff actually addressed some of the comments I was going to make. I just wanted to reply to a couple of the questions that came up earlier. The first one is the BAU. So yes, for the Nelson Way result, the definition for BAU is somewhat different. It is, we called it the frozen efficiency BAU electricity scenario. So it's actually a scenario where we keep the efficiency levels frozen for buildings, industry, and transportation, but the electricity sector emissions are frozen at the 2020 level, which is the 33% RPS level. So it's a little bit of a hybrid, but then we apply the energy efficiency measures to those sectors, and then that brings us down towards our target. The second question was just the energy demand question for transportation in 2050. And I think that Chris Yang addressed that in part, but I think just wanted to make maybe the obvious comment that the energy demand for 2050 and for 2030 will be very dependent on the assumptions, of course, and specifically the assumptions for the vehicle mileage, the VMT traveled over time and as a function of the vehicle lifetime, and also the vehicle sales or the vehicle ownership. So, there have been some trends which suggest that those are flattening or reducing, but it's really an open question of what those long-term trends are. And at least for our model, the leap switch model, we kind of hardwire some assumptions in, so that will kind of set the final energy levels into the future. And then for the biogas, I would agree with both the comments that have been made by Chris and by Jeff. And just one other comment I would make for the research needed or some of the gap analysis. I just wanted to comment that we haven't talked about the industry sector, and the industry sector is, it's not a huge sector in terms of overall emissions, about 20% currently, and they've been dropping. But there's also the fact that some of the industrial emissions could be outsourced or offshored, and so there's a leakage question and how to treat that and how to really include that. Because in the future, if we just look at the in-state oil production or other industrial sector production like cement, which may be leaving the state, then those could look artificially low. So I just wanted to raise that as another issue among many. Thanks a lot, Max.
So we have a few more questions in the queue here. We'll see if we can get to them. We have about 5 more minutes left. The next question is with respect to sort of the upstream life cycle emissions. And the question is, electricity is the only imported commodity with GHGs accounted. I guess that's either a statement or question. Low carbon fuel standard could account for greenhouse gas emissions of imported crude oil supplies. And can you summarize the modeling efforts to incorporate life cycle of all of the energy flows?
Yeah. I think it's probably best the model developers answer that.
So this is Chris Yang for California Times. We actually track some of the upstream, what we call upstream emissions associated with bringing in, importing natural gas and various other resources, biomass from outside of the state and so forth, and crude oil as well. So we do track emissions from those sectors and those activities, and we don't include those in the carbon cap because those aren't included in kind of the state's carbon cap. But we do track all of the emissions associated with the production of and consumption of energy within the state. So
that the emission is a really important question. Jeff didn't. It's summarized in the report, but Jeff didn't explicitly say that actually system boundary is an important factor when we do the model comparison. Various models cover different sources of emissions and count different categories of emissions that partly contribute to different results that we see in the mitigation efforts. Like Chris said, that California at times we tend to do consumption-based emission accounting, but when we do the policy analysis, we use different types of emission accounting. Vision model is another model that tries very hard to do life cycle emission modeling. So emission accounting definitely vary across models, and it's an important characteristic that affects modeling results and policy recommendations as well.
Excellent. So I think actually we're sort of nearing the end of the time here. I just want to thank all of you for taking your time out of your day to listen to the webinar. Again, all of the materials, including this presentation, are posted to our CCPM website, and we'll put that up on the slides here. And if you do have any further questions, you can either send them in to myself, areggert@ucdavis.edu, Jeff Morrison at
gmorrison@ucdavis.edu.
Yep. And then also, you will get a little opportunity when you log out online of the Ready Talk. It'll ask you a few sort of survey questions, actually just one particular survey question. We may also be sending a follow-up survey to ask a few more. We're very interested to hear from you about how we can make this project valuable to you, and look forward to sort of continuing this effort. And I would just encourage you to sort of keep an eye out for future webinars and future publications that are specifically focused on this question. And then finally, I just want to really emphasize a very, very strong thanks to Sonia, Chris, the rest of the team, and certainly all the other modeling groups, as well as the steering committee that helped shape the forum that we held on this topic. All right, I think with that, we'll bring the webinar to a close, and thanks everyone. Have a great rest of your day. Thank you.
Thank you. Please stand by.